Everybody, and welcome to our last press conference of this General Assembly. This is EGU25. It is the second largest General Assembly of geoscientists and geosciences in the world, and the largest one in Europe, where we exceeded 20,000 people attending both on-site and virtually. So today the press conference is titled Floods and Future Fears, Our Planet's Escalating Climate Hazards, where our speakers will explore insights on the impact of heat prevention strategies in reducing heat-related mortality across the regions. So we will learn about the urgent need for climate adaptation and innovative solutions to protect our communities from the escalating risks of a warming world. So today we have Andreas Schaefer with us from the Risklayer GmbH in Karlsruhe in Germany. And we have Aleš Urban from the Czech University of Life Sciences in Prague, the Faculty of Environmental Sciences in Czech Republic. So thank you so much for joining us, and thank you.
Thank you so much for the interest in the topic. I want to talk about Europe's exposure at risk. So early this week, we had this huge blackout in Spain and parts of Portugal. And imagine if on top of such a blackout, there would have been a flood like we had seen last year in Valencia, or an extreme heat wave. So during a blackout, there is no air conditioning. So the risk of heat for people would be heavily increased. And questions like that, so what happens when we have two disasters occurring at the same time, overlapping to some extent, those are questions that we are asking ourselves at Risklayer, but we also ask that within the Myriad EU project. The Myriad EU project has the goal to bring together the understanding of natural disaster risk, how they occur maybe together and singular, and the impacts, for example, in sectors like tourism, agriculture, and infrastructure. And this is done also by having a development of a lot of tools, a lot of data, and sharing that also as much as possible with the public, and doing that with a lot of stakeholder interaction in various pilots. Where our role came in as Risklayer was, especially in the beginning part, there's a whole framework of how to do that. And when you talk about risk, you first have to define what risk you're talking about, so what is actually affected. So we are defining a system that's affected. We call that the exposure. And when this exposure is interacting with natural hazards, things that occur there, then we are talking about the risk. So let's get a little bit into the definition when we are talking about risk, because there are sometimes a few misconceptions. So when a disaster occurs at some place, it's not necessarily a disaster, it's a natural phenomenon. Only, so it could be a storm, a flood, an earthquake, whatever occurs. But only when this event actually interacts with that what we call exposure, for example, people, homes, or our businesses, then we are starting to talk about risk. And the glue between both of them is something we call the vulnerability. So, for example, when you have elevated temperatures, different demographic groups, for example, elderly, are more susceptible to heat stress than for example, 30-year-old people. So bring all this together, we define as a risk, and the risk is always the outcome in the end of a certain kind of a loss. So something has to be destroyed, damaged, or lost. But getting to the point of calculating that can be very expensive. It can be time-consuming. There are a lot of uncertainties in it. So to get a very first-level understanding of how the risks in Europe look like, we actually skip the part of the vulnerability to increase the feasibility, to get a European-wide perspective on as many hazards as possible. This way, we are avoiding uncertainties, because defining the vulnerabilities can be, like I said, very expensive, very time-consuming, and needs sometimes a lot of assumptions. It also provides us an easy-to-read metric, because we're not talking about a certain kind of loss that's occurring. We're talking about, for example, the amount of people that are affected by a flood, or the amount of productivity, like the GDP, that's within a power outage, for example. And this allows us, within a reasonable amount of time and workload, to actually provide a large-scale assessment of these risks affecting our exposure. So starting at the hazard perspective, there are a lot of different disasters that can occur in Europe, and there have been a lot of projects already assessing them. So what we did at the beginning of the project is actually collecting all this information that's available openly out there, maybe not known to various people out there, but that has been generated in a lot of amazing projects in the past. For example, the RAIN project or the ZooMaps NEAM project that addressed tsunamis. The Sarah PSHA project, which provided us a lot of insight into earthquake activity in Europe, and many, many more. So we combined that. In some cases, we also added our own expertise at Risklayer, so complemented these models with what we do in our company, and combine that with a definition of a lot of different types of exposures. Of course, the easiest exposure to talk about, that's people. That's the amount of people that are there today, but also how could be the population in the year 2050, depending on different scenarios of, for example, population growth and so on. But we're also talking in a similar way about the productivity, so the GDP today and in the future, and a little bit more abstract, the capital stock. The capital stock is everything that we have available as a society or as a certain business sector at our use. For example, when we're talking about the capital stock in agriculture, that's not just the crops that are out there on the field, that's the machinery that's used to harvest it, that's the buildings involved in that, the factories that are needed to produce the food in the end. So there are a lot of different elements coming here together where we can identify what is actually affected. And to be a bit more in detail on certain sectors, so we had some specific areas where we went a bit more in detail. So we also looked at the tourism indicators, so how much expenditure is taking place with tourism activity in Europe affected by disasters, and agricultural productivity. And we aggregated all this information primarily on, we call that the NUTS 3 level. That's an official definition on like a county basis all around Europe. And but the original data behind that is actually on a very high resolution level, so 100 meters. So we can really drill down in what is happening there and bring that together with hazards, which may be on a similar resolution, for example, very important when talking about floods. Not so much about earthquakes, for example, where it's not really a difference whether you're 1 kilometer further apart or not. And we brought all of this information together in one consistent framework, normalized all of that. And some example outcomes are, for example, that about 400 billion euros of agricultural capital stock, so again, it's both crops, machinery, and the buildings involved there, is actually in regions where we have high water stress in Europe. So regions where droughts can be extremely harmful. So water management here plays a crucial role for our agriculture, both today and the future. Another example that can come out of that is that about 25 million people in Europe are affected by heavy flooding at least once every 50 years. So that doesn't mean that occurs every year, but within the lifespan of, let's say, a generation, which is about 50 years, about 25 million people should expect flooding of at least half a meter. And by taking into account different developments of population and also taking account what could, for example, climate change do on the return period of flooding, depending on the place we're looking at, this can increase by another 20% by the mid of the century. So this is just a few examples of what can be done. I mean, there's so much more behind that. But we're not only looking at singular hazards, we can also combine different hazards together and compare them. So, for example, we can take a look at what's the bigger threat to our manufacturing industry in Europe. And maybe surprisingly for some, earthquakes are a bigger threat for all of Europe for manufacturing than floods are, because floods are spatially, of course, relatively limited, so that many factories are affected at once is less likely. So talking about flood levels or ground motion that could affect, for example, business interruption in a factory, we are talking about more than 10% in Europe being prone to earthquake risks, and only about 2% being prone to flood risks. And this is increased. So when we're combining both hazards together, we're talking about 1.5 trillion euros that could be disrupted by either earthquakes or flood occurring there. And on the other side, we can also take a look, for example, tourism. And yeah, about 14 to 15% of tourism is affected either by high levels of wildfire or high levels of drought being located there. So that means a lot of tourism activities taking place in regions where drought and wildfires are a common threat. And if you combine them, this number is even increasing more. So again, this elevates the necessity of good water management for these industries in many places in Europe. These are just, like I said, a few examples. So we assessed more than 20 primary hazards and we keep growing. So we want to maintain this database and actually web platform. All this data is open, aggregated on the NUTS 3 level, and also the web platform is open. All of this will be released this summer. So any stakeholder, person of interest, a journalist, or an expert who just wants to start at a certain topic can go there and get a basic understanding of first figures of how relevant are certain hazards to certain exposures in Europe. And aggregating all this data together, we are already talking about more than 30,000 individual data points for every single county within Europe. And this is ever growing and could be then the starting point then for further research, further projects, further investment in better understanding what risks Europe is actually facing today and in the upcoming decades. Thank you.
That was brilliant and also thought-provoking, so thank you so much. And now we are going to move on to Aleš.
So hello everyone, and thank you also for inviting me to this press conference. My name is Aleš Urban. I'm from the Czech University of Life Sciences, and this study is a result of our cost action Prouklias, in which focus on many different aspects of climate change attribution and attributing different hazards to climate change. But in my specific task group, we focus on the integration of adaptation measures to heat-related mortality studies and basically to analyze the efficiency or effectiveness of heat adaptation measures and specifically heat warning systems in my case. And so together with probably, yeah, as already Andreas mentioned, like the heat is really quite, let's say, hot topic and severe climate hazard that everybody can see that basically every second year is the hottest year on the record, and or at least among the top 5 hottest years on the record. And also, for example, in 2022, maybe some of you mentioned this, noticed this study that the heat in 2022 caused more than 60,000 heat-related deaths in the whole Europe. And it shows the right-hand panel, and the left-hand panel shows that basically we can see, especially in the last decade, we can see increasing frequency and intensity of heat waves in Europe, and basically every year, basically the slope of this increase of the intensity has increased, like especially during the last decade. And of course, like the question is, how can we adapt or how can we avoid these excess deaths? And one of the answers are, one of these responses and like considered as probably the most efficient adaptation measure are these heat warning systems or heat prevention plans, which include more, let's say, there are several terms: heat warning systems, heat and health action plans, heat wave action plans. Like different countries names these plans in different ways, but basically the main definition is that these heat prevention plan consists of 2 main parts. One is like, let's say, the heat alert system that really is basically the forecast of that tomorrow or next week there is going to be a heat wave, and people need to prepare for it. But also these heat action plans include the actions after the heat warnings. That means like basically some steps or some actions after the heat alert that basically the vulnerable groups are taken care of. Hospitals have some special action plans, and basically, so these, like the full heat action plans, are not only about the heat warning but also about the actions taken after the heat alert. And yeah, and several studies previously, several studies basically I like studied this the potential of the or the effectiveness of in reducing the heat-related mortality risk due to heat warning systems, but most of these studies focus only on single cities or single countries, and they usually also studied like quite basically small region or some short period. So but even these studies basically still highlight that there is still quite uncertainty in this effectiveness or in the conclusion if these heat warning systems are really effective in reducing heat-related mortality risk. And so basically there are still many limitations, and in our study we tried to, let's say, overcome some of these limitations the way that we included basically locations or more than 100 cities from Europe and from 14 European countries. That means that, yeah, basically this is probably one of the first continental-wide studies that really consistently analyze the effect of these heat warning systems across different countries and different, let's say, regions of Europe, and using like consistent methodology and consistent data set to basically to get some overall effect across the Europe. So we use this weather and mortality data available via the multi-city, multi-country collaborative research network that I'm part of, and where we have access to these mortality data. And also via the partners in the cost action Procrias, we collected the information about the heat warning system and heat action plans in individual countries. And we basically collected information about the implementation years and about because of course like there is like not all the heat action plans are same like across Europe. In different countries they have different level of complexity, different elements are involved in this heat action plan. Sometimes they include only the basic heat warning, especially in the colder countries like Northern or Eastern European countries. They basically usually just issue the heat alert, but there are no really these action after the heat alert taken, while especially in the Western countries like France or the UK or the Southern European countries, these systems are more complex, and they also include the follow-up steps like to basically regarding the vulnerable groups and other elements. And you can also notice that especially in these countries like France and basically the Western and Southern European countries, they basically most of them or many of them implemented the heat action plans after the 2003 heat wave, which was basically quite infamous year in terms of unprecedented heat wave and unprecedented impact on heat-related mortality, especially in France and Western Europe. And it basically motivated many countries, especially in this southwestern European region, to implement these heat action plans and to basically to protect the population and people from the adverse impacts of heat. And so in our case, we collected this information from these different countries, and I will not go into the detail of the statistical modeling, but basically the main part of this is that we analyze basically we compare like the heat-related mortality risk before and after the implementation of this heat prevention plan in the given country, and compare basically the risk of the heat-related mortality before and after implementation, and we adjusted this effect for the long-term trend in heat-related mortality risk in the individual region. Because one thing is this effect of, for example, that after implementation of a heat warning system, there is a decreased risk of heat-related mortality, but still in all countries, or especially, I mean, basically in all countries, there is some overall trend in this heat vulnerability because of changing demography and many different things that are not really related to implementation of these heat warning systems, but they are basically just some, let's say, natural adaptation or acclimatization of the societies to the climate, but you can also see that, especially, for example, in the northern and eastern European countries, there is actually increasing trend in this heat vulnerability, while in the Western and Southern European countries, there is rather decreasing trend in this heat vulnerability. But basically the point is that we adjusted the effect of these of the implementation for these overall trends in the data. So yeah, hopefully the final conclusion should be let's say adjusted and somehow more objective and yeah, consider this overall trends in the data. So, and this is basically the main result. This is for Western Europe, but we did it for all the European regions, but it compares the heat-related mortality risk in this counterfactual, which basically is the effect if there was no heat prevention plan in the region, and the factual scenario is basically the real exposure or the real heat-related mortality risk if there was implemented the heat prevention plan. So basically, this is, for example, for the Western European region, where the difference was, let's say, most significant, or the evidence was strongest. If we look at the other regions, you can see that the uncertainty is higher, and let's say the confidence of the protective effect is lower, but still in all the regions we can see a decrease of the heat-related mortality risk after implementation of the heat prevention plans in all the regions. So basically then we compared, based on these exposure response curves, we compared the excess mortality attributable to heat based on these functions, and the main conclusion is that basically the implementation of heat prevention plans was in total associated with approximately 25% reduction in excess deaths attributable to extreme heat, which was equivalent to approximately 15,000 total deaths avoided across all the study locations. That means these 102 locations and the years. But on the other hand, because we also considered like these different levels, because we also run the typology of the heat prevention plans across the countries, and then we also, in some sensitivity analysis, we also analyze the effect of the different level of the complexity of these systems, if it helps to reduce the heat-related mortality risk. And actually the statistical models didn't show any evidence of this or any significant effect. If there was a better level of the heat prevention plan, that would be higher reduction of the heat-related mortality, which suggests that there is still a lot of to understand and to explore. And yeah, basically it's still, there are still many uncertainties also in the data collection, especially about these heat prevention plans. Of course, we use mainly the open source data and basically in internet and in some documentation. And one thing is what's online available or what's in these documents, and the other thing is what is the reality and what is really implemented in these individual countries. So yeah, I will end here, and thank you for your attention, and happy to answer any questions.
Thank you so much for your presentation as well, both of you. It's been very educational, and I cannot wait for the platform to be available this summer. Maybe I'll reach out to you then. I want to open the floor to questions, but I want to kick off with a question of mine. So you studied and you researched and got the results about exposure and about risk. But what I want to know, the models that you used, have you used gendered or racialized lenses when it comes to Europe? Europe is a pluralistic society. So have you considered that whether this risk and exposure is affecting people differently based on their racialized backgrounds or gender or a migrant background?
Not in this detail, to be honest. So we're just looking at population in general. But of course, not in this project specifically, but we're of course doing a lot of other work also within the MIRATE project. So the term of social vulnerability, and which specifically addresses then, for example, societal minorities, is a key factor when we are, for example, then addressing the resilience of a certain place. This is not addressed in this framework that we provide here, but there are other, let's say, deliverables. We are looking in much more detail, but all of Europe all at once, that would be, let's say, a little bit beyond the scope of what is doable in this project. But yes, it is a very, very important part in really increasing the resilience of our societies against natural disasters.
Yeah, I have similar answer that for this specific study, we didn't have this micro data or the individual data to analyze this, but from previous studies we know, and it's been, I mean, in many countries, many studies, it's been known that, for example, women are more vulnerable to heat than men, and of course elderly and children, but especially this like women-men differences is quite obvious in many countries, and also one of my student actually ran this kind of analysis for the Czech Republic, and for example found some quite interesting differences between that. For example, divorced women were at higher risk of heat-related mortality than divorced men. So yeah, like maybe I will not really go into details now, but yeah, basically it also suggests that there might be not only physiological differences, but also some social differences, and basically, yeah, like the social inequity in the results that affects the differences between men and women in this heat-related vulnerability.
Absolutely. Thank you so much. So do we have any questions, whether online or offsite? On-site, sorry. Yeah.
Hi, thank you for this. So I want to ask you, you gave some examples of where the exposure will increase because of climate change, but presumably the hazards, the sort of likelihood of the hazards is going to go up as well. Is that factored into your calculations? And then if you put that together, the you know, how much is the risk of these sort of multi-pronged disasters? How much is that increasing? Have you looked at that at all?
It depends on the disaster, of course. So for some, it is possible to quantify, of course, the change in of the hazard in general. For example, heat, we have changes in patterns of precipitation, changes in pattern of floods. So this is where data is available and sufficiently reliable. We also have to add there, is taken into account. So that can also be assessed. And on top, we can also then compare the population of today, population of then in the future. Also, what if the future is with the population of today? So there are then different metrics again, which can be pulled out of that. So this is to some extent included, not always possible, to be honest, because just the uncertainties are too high. But wherever it is feasible, we try to cover that. Yeah.
And then I also wondered, are there any examples of historical examples of sort of where there've been multiple disasters at once? Can you mention any?
I mean, when you have to be honest, I cannot recite a specific event, but it's a common feature in many, for example, flood events. For example, in the Ahr Valley flood, we have, of course, the flood itself as a big issue, but of course, these precipitation events, they also trigger landslides. So we have local erosion effects, effects of subsidence, for example. We have, depending on how you want to define then the multi-risk nature, we have not only the water as a risk, we also have the content of the water, the debris that can kill people then in the flood. So yeah, let's say the definition of multi-risk can be very, very detailed in terms of how many elements can then be like a cascading effect in causing damage or harm people. So yeah, and in the end, many disasters like a storm surge event is by nature multi-risk, because we have the surge, so we have rising sea levels, maybe have sea level rise on top of that, then we maybe have to consider tides, but on top we have heavy rain that's affecting the region, plus we have often strong winds, so we have at least 3 hazards interacting at once, and sometimes we have just long-lasting hazard events, which we not even probably define with start and end, like a heat wave. And then within a heat wave, we suddenly have a severe convective storm, like a thunderstorm causing a flood on top of that. And of course, where you have multiple risks interacting, you also have then often an increase in vulnerability of either assets or people.
Thank you.
Do we have any other questions?
So first, a question for Risklayer. So this model is not being used to assess risk. Is there a potential in this model to also in the future, given if you are given the data to assess impacts of potential adaptations?
Technically, would be possible in the future. The question is whether that could be done in this European-wide framework, because often then the local setup plays a very, very crucial role. So, so what we want to deliver here is especially like this first step, where to start actually with the work, and then going into detailed adaptation measures. Then we are talking about much higher workload that could be done in such a framework.
It's too complex for this Europe-wide.
And as of now, it is. Of course, you can measure certain elements of like on a qualitative basis, like on an indicator basis, and then combine that with qualitative identification of vulnerabilities. And for example, like the best example we just had here. So it's the implementation of heat protection plans, for example, and this you can then consider then as future pathways if these things are implemented, yes or no. So you can also adjust then the exposure.
Thank you. And then a question for you about the heat related deaths. You had that graph on, I think, slide 8, where adjusted for heat related death trends, the impacts of the HPPs. And so, as you mentioned, the Northern European countries are still kind of trending upwards. So that's even with the heat protection plans in place? If I understood, I'm not sure I understood the
Yes,
graph
but
correctly.
basically this, because the thing is that these are basically two different things, right? Because one thing is that, in general, because of, I guess it's related to many things, demography, and maybe also basically the variability of the heat waves that in different parts of Europe, the major heat waves occur in different years. But so basically, especially in this northeastern part, like the major heat waves, for example, this 2003 heat wave wasn't that impactful in this northeastern European part. It was more in the southwest Europe, while in the eastern Europe we had like more, like for example in 2010 there was a major heat wave, or later. So basically these, and also probably some demographic trends that, again, especially the Eastern European countries have, I think, this high trends in aging population, and basically so to answer your question, that these are some trends that basically are not affected by implementation of heat prevention plans or anything. They are just based on some trends in the population. And then and the point is that many studies, or probably not all, but like some studies in previously, for example, just compare these, let's say, crude heat-related mortality risk before and after implementation, and didn't consider these background trends, which are not, or that are not related really to the basically to this implementation of the system, but to the overall trend in the sensitivity to heat. And so I'm not
So your graph was really only the one variable, right? So only the implementation of the HPPs.
So so basically the one graph was the implementation. So and the one with the two curves, like the counterfactual versus factual, was adjusted for these overall trends. So basically it's like the effect of this implementation without this general trend in the heat.
So I mean, on slide 8, you had like you had the different regions of Europe kind of converging from the southern on the top to northern in the bottom, kind of converging. Where then, if you look at the trend lines, the northern countries are still trending slightly upwards. Even that's the one I mean. So I was just wondering, I suppose it's if you have any input on why the death numbers would still be trending upwards in Scandinavian countries, even with implementation of HPPs.
It's I think to be honest, probably the main reason is because in the study, for example, we had, because we have data from different countries, and we didn't have the same year span for all the countries, and so, for example, for these Western European countries, we didn't have the most recent years, while in these Northern and Eastern European countries, we actually had these, let's say, more recent years. So that might be one reason that basically, in general, let's say the last decade, or from 2015 to 2020 was quite hot in whole Europe. And if we include these years also for the Western European countries, we like the trend maybe wouldn't have been so decreasing. But the other thing is that also, even if we consider the same years, still, as I said, like the heat waves or these major heat events occur in different years. So of course, like we can implement the heat prevention plans, but still, if there is a major heat wave in 2020, it will have a larger impact than like some previous or colder year. So I think like that's the main reason in these different trends, that basically the dynamic of the heat waves is different in the regions. And another reason could be also this basically the different demographic trends, that some populations are basically aging slower than other populations. But yeah, I mean, it's quite complex, and probably there are many reasons behind this. But yeah, I mean, I guess like probably the main reason is this different dynamics of the heat waves in different parts of Europe. That basically, yeah, in the same year we don't have heat wave across the whole Europe. It's in some part, and another years it's in another part, and then it depends like where do you have these major heat waves in the given regions in the time series.
Okay, thank you.
I don't know. Can we see it?
Okay, and we have a question online, which I cannot access unless you stop sharing the screen.
So can I talk or no? Yeah, because it's like this is basically this table shows what data like the cars shows what data we have available for which regions. And so, for example, in these basically these most recent years that are hottest, we had data available from, for example, from the UK, from Czechia, Poland, Serbia, but for example in France we had data only until 2016, and in most of the countries actually we had data only till 2016, while basically these most recent years were yeah, basically, for example, in Portugal, if I look only on data from Portugal, there was also like again like slight increase in the latest years in the heat related risk. So yeah, but I think like in general we can say that it's probably also related to this presence of the 2003 heat wave, that in these Western and Southern European countries there was like really huge impact of the 2003 heat wave, and basically that caused this decreasing trend, because the later years were basically not so hot and also not so impactful as the 2003 heat wave, while in these northern and Eastern European countries didn't really have any event like this before. And then, like for example, in 2015 there was quite major heat wave in the Eastern European part, so that probably caused the rather increasing trend in this part of Europe, while in the Western part, like the major event was basically in the earlier part of this time series. Yeah. Yeah, I think it was for, oh, not, it wasn't for Scandinavia, but it was, yeah. But yeah, the thing is that these trends probably will change or are have been already changing, and yeah, like the actually data from the countries from where we have the most recent data suggests that basically the trends are increasing, and yeah, I don't know if
No need to be sorry. No, we're actually here for that. So we have Stefano with us online, and we are having problems viewing your question. So would you mind just copy pasting it again in the general chat, please, Stefano? So not directly to an EGU account, but in the overall group? Okay, perfect. I can see the question. So the question is for the panel, for both of you. And Stefano is saying, is it possible to quantify deaths as a linear or non-linear proportion of carbon emissions leading to temperature rise and ultimately to heat waves?
That's a good question. Yeah. Thank you for the question. But I'm not sure if I'm able to answer this kind of. But I think there is a probably not linear, but definitely, as I suggest, there is some correlation, of course, between the intensity of heat in a given year and the amount of heat rate are quite strong correlation. But I mean, not 100% because, of course, it depends on the vulnerability of the population in the given years and many other aspects. But in general, there is quite strong connection, of course, between the intensity of heat and basically the general, let's say, level of warming and the amount of people affected by the heat, and that means also about the number of heat-rated excess deaths. So I guess from this point of view, there is also probably also a link or some correlation between the level of CO2 emissions and the amount of or the impact of heat waves on public health in general, I guess.
Yeah. I mean, I can agree. I mean, theoretically, you can definitely do that. It's just, of course, a matter of, how difficult it actually is to get that right, and also with the uncertainties in it. In general, you can definitely say with the ongoing heat increase in temperature worldwide, but specifically in Europe, we're already talking about an exponential increase. So temperatures, the occurrence of very hot days in almost any country in Europe will increase exponentially over the next decades. And so we can also assume that the risk of heat is increasing similarly exponentially. So the relevance of, for example, the heat adaptation plans become even more relevant. And the question is, can we keep up with adapting us to this changing climate? Or is there at some point a cost in implementation of these plans that are unbearable for society and reach maybe then the point that where the risk and the cost are just, mitigation would have been cheaper. But that's something we might need to evaluate in 50 years, but should ideally know today.
All right, thank you so much. And also Stefano says thank you to both of you. So do we have any other questions on site or online? Nope. Well, that brings us to the end, not only of this press conference, but about the series of press conferences that we have scheduled for you. I just want to remind you that if you're watching this online and you have missed any of the press conferences live, that you can find all of them recorded on our YouTube channel. And I also want to give a special thanks to Aleš and Andreas, so let's give them a round of applause. And that is the end of our press conferences. So thank you so much for attending.